Good afternoon. I invite you for the 9th lecture of our course, and today's lecture is about connection of the computer system to the external world and sensing and reacting to some external events. So we have already seen what are the building blocks of the computer. So we have some central processing unit. It manipulates with the data, and data are stored in the memory. The fastest possible storage for the data is directly inside the processor in the register file. It is under the control of the processor, what is and what is not in the registers. Then there is a main memory where we organize data as we want to use them and as they are somehow logically interconnected and so on. But the main memory is slow, so there is a transparent L1 and L2 cache, which is in the fact hidden memory, which automatically keeps the data which are near to the data which we access or which are there for the next access. So this is the temporal and spatial locality, which helps us to speed up processing. And then we have there some relatively slow external memories like disks and SSDs and so on. And we interconnect the subsystem of the computer through some buses. So it was the topic of the last lecture. And today we can see what are all those stuff and building blocks good about. So we want to use computers, for example, for the entertainment, so for video games and so on. And in such case, we need relatively high throughput and possibility to process 3D graphic and so on. So in the fact, at the start, 3D graphic solutions and hardware acceleration has been implemented for computer aided design application, then for animation for a film. Then it gets into the consumer segment as GPU cards for video games and so on. And then this technology, which advanced to draw fast 3D images, has started to be used even as accelerators for common computation. So it is general purpose GPU computing on NVIDIA cards and artificial intelligence and so on. So this is one area of enhances in the computers and its use. Then another is a big enterprise application like stock exchange and, for example, New York Stock Exchange, London Stock Exchange, enterprise application and so on. So there you need a relatively big computer system, bank systems and so on, and enterprise customer relationship databases and so on. And then we have a little different area which needs a large-scale mathematical computation like a global warming prediction or weather forecast or nuclear fusion and other stuff, modeling and so on. So it is big systems with high computational power. But what is interesting on those large-scale computation is that it is possible to optimize them that they have relatively long segments of the linear code. So they are in the fact in some respect easier than that business application which has many conditional instructions and so on, because in the typical business application each 6 or 7 instruction is some condition or jump. In that video, it is interesting that it is possible to run some of those computations in parallel, because it is in the fact same operation to compute on all, for example, element, to compute the scattering of the light on some faces and so on. So it is less intensive in the branches, but sometimes you need, for example, to branch or to stop processing of those elements which are hidden by some others and so on. So each of those areas has different demands on the throughput and for the components of the computation. And today all those systems are interconnected through the communication. So even that communication can be standalone area for the computers, then even all others today needs the communication as well. So some fiber optic and so on. And there are many other uses of computers. I am from Department of Control Engineering, so there are some robots, models, and so on, which we have done with Linux operating system and other real-time operating systems. So at the moment when we start to look at the computer system as the controller which controls the state of some plant, then we can look at it through the classical control theory. So in the case of control theory, we have there some input variables which are not directly controllable. It can be, for example, external temperature or sun power or sunlight and so on. Then we have there some disturbances in the measurement and some stuff again which cannot or which provides a noise, which basically influence the state of the system. And then output can be, for example, some temperature inside building, outside of the building, spreading of the heat, and so on. And if we can sense some part of those output variables, then we can use it as a state information about the system. We can somehow interpolate and estimate the state of the system and use a computer as the controller to control such controllable inputs of such system. So basically we can, for example, follow the line or something, control the helicopter. This one was with the small oil engine, so it was relatively interesting stuff which we have done here, and so on, and many other systems. And why the computers are so common used in the control systems? Because in the past there was analog controllers usually built for exactly that one application, and there can be pneumatic, electric, and so on. But problem is that if you want to control some plant, you each time need to build a new control system, tune its parameters, and so on. But at the moment when you use some computer as a controller, then it is much easier to control the complex system with many inputs, outputs. You can use units which are produced serially, even for different plants, so it is much cheaper. And actual control law, actual controller implementation and algorithms can be very easily reprogrammed or even remotely tuned and so on. It is possible to use a hierarchy control, so for example that you have some low-level controller for the engine, for example, for electric car main engine, the AC motor or something like that. And then you can use a digital communication with upper level, which, for example, controls the braking and so on of the system. So hierarchical possibilities, and in the big production factories and plants, it is even much more important that you can use a hierarchy, that you have some small controllers connected to each motor, and then you can have some other coordination on higher level and so on, which demands, for example, more computation for example, today even artificial intelligence and so on, and can use some communication links to send the commands to some lower level controllers. And another advantage of the digital and computer-based control is that it is easy to deliver the information to some display, and that you can record the values and so on, because you have them in the digital form. So if you do not have so big disturbance that your memory stops to work, or you cannot distinguish 1 and 0s, then basically the information is stable. On the other hand, if you use analog processing of the process variables, inputs and outputs, then you have problem that there is noise, and that analog memory is relatively problematic stuff. So it forgets the information, same for example like a dynamic memory. So the digital control has big advantages. On the other hand, be careful, we have seen the problems with the limited precision of floating point representation. So at some moment, if you add the 1, for example, steadily add 1 to the value in floating point representation, then at some moment, about 16 or 16 millions, you stop adding the 1. So if, for example, if you compute the time in nanosecond and add 1, 1, 1, 1, then it stops work. So be careful. It can be really big surprise if you do not understand well what it means to compute the stuff digitally. But anyway, you can have complex algorithms as large problems as fit into the memory. So only limitation is the memory and time. To have some idea how fast we can solve the task on the computer control task, then if we speak, for example, about GNU Linux system, then the standard kernel has no real-time and latency guarantees. So the time can be quite large. It usually computes stuff very fast and communicates very fast, but sometimes there can be a lag. But there exists the real-time variant of Linux kernel, some adaptation, which are slowly getting even to the mainline. When this adaptation makes the kernel little less responsive, it's a little smaller throughput, but with almost guaranteed latency. So on the standard x86 computer, if you are happy and do not have a buggy BIOS and other motherboard problems, you can get to the maximum measured latencies about 30 microseconds. So we have done the control at 30 kilohertz by the regular PC with Linux and MATLAB Simulink generated code. So on the smaller ARM-based processors, we get to something like 150 maximum microseconds latencies. So something like 5 kilohertz with control with our, for example, MZ Apo boards or some other stuff is possible if you have a real-time kernel. With some real-time operating systems, smaller real-time executives, you can get even faster, but below 10 or 1 microsecond, it is a big problem to get directly by the software. So in this case, if you want to go lower, you probably need to implement your own logic design in some field programmable logic devices, or combine it with processor stuff and so on. Okay, so in the fact we can look at the system as and computer system at the data flow model. So basically there are some inputs, there is flow of the information to the usually main memory through DMAs. So usually it doesn't go directly each byte through the processor. Then we process the data through the execution unit, control units, and so on by processor. And then there is some data flow which goes out. And today's lecture we focus how to efficiently inform the processor that there are new data and that some data should be processed and so on. If we look at the typical processing of the data, then it can be something like batch processing. For example, if your accountancy company gets data and it should provide a result, then it can be a batch process basically, and it is not important when it is processed in some, if it is it fits to some deadline, so for example day or something like that is not a problem, but you need to process a large amount of the data fast, so it is batch processing. Then you have interactive, when maybe it is not necessary to process so much data, but the system should be responsive, because for example if you move the mouse and it doesn't process the request in a minute or in a second, then you start to be nervous. And then we have a real-time application which doesn't directly mean that it has to be extremely fast. For real-time definition, it is important that if we analyze the application and decide that we need to deliver a result in some time, that the data are delivered in that time. So usually real-time application do not demand so high throughput, but there has to be guaranteed latency that we do not miss the deadlines. Basically, if you, for example, control airplane and do not solve the task, controlling task in time, then maybe you have crash. You can have soft real time, for example, if it is for the multimedia, for video and so on, then if it doesn't solve the refresh of the frames fast enough, then you have there some missing frame or some glitch and so on, so it is not so big problem. But for hard real time, basically you can, or there is a risk that somebody is killed or that there is a damage. So it is, those applications are sometimes quite demanding. Okay, we have already seen that there can be a input-output subsystem. We have spoken about input-only peripherals, but said that today, for example, the camera has two-way communication. But in the fact, this one, for example, which I have here, is only HDMI output. So it is really single direction, but there is possibility to connect it to another link which allows to control it, or it can be controlled remotely. So, for example, this camera is special one that it has only the output. Typical cameras which you have webcams and so on are connected through USB, and you can directly control the focus and brightness and other stuff directly through the same interface through which then flow actual images. So today usually the communication is bidirectional, so we can have input-output peripherals, okay, and most is bidirectional. So we have looked how to connect a simple peripherals to the system on the last lecture, during the last lecture, and now we focus how to wait for data. We have seen that simple so-called polling solution where we check if the output TX register is ready to accept a next character. But this mechanism wastes a lot of the time because CPU, which is usually fast, needs to do many cycles where it checks that there is no space to write a data to be transmitted. Or on the input it is even worse because you test, is there a new character, and if nobody press, for example, a key for a long time, then you waste all the processor power and cycles on the checking if there is an input event or not. So for this reason, most of the processor system are equipped by some mechanism which allows to notify a processor about the external events, maybe input, output, or some errors, overheat, and so on, asynchronously. So basically, program or operating system configures the peripherals, but doesn't wait for the actual data, and set up the mechanism which delivers the interrupt or exception of some another background processing to the CPU. So basically you process some another task, you can do computation, draw the graphic and so on, and when the data arrives, for example over the serial port, then the exception comes and you can read the actual data. Again, this mechanism was quite common and it is used, but for a large data throughput, for those channels which needs to deliver megabytes or gigabytes of data per second, this is not good idea because each byte which comes needs to be processed by the CPU and stored into the memory. And usually it is only the stored here, and then when you have, for example, a whole input line, then after the last enter, it starts to be processed by some shell or something like that. Or from the disk, you get a sector after a sector, but until you have a whole set of sectors, you do not start the actual processing. So for this reason, it is better to set up some mechanism which allows the periphery to store data to the memory automatically, and then you get a interrupt, the notification that, for example, a whole packet or whole set of required sectors from the disk has been read and stored into the memory. Or for the output peripherals, for example, you set up a buffer with output sample for audio output for the speaker or for some audio subsystem. And when, for example, half of the buffer is played out, then you add the new block, new interval into the memory and set that when the next piece of data is played, then it will continue by your new data. So basically, you have there some FIFO-like mechanism which ensures that even if there is some small lag in the CPU, that you do not make a gap in the output sound, but you basically keep the FIFO somewhere between half and full fill. So this is the mechanism which use a DMA. Okay, so we return back to our basic CPU cycle, and we have said that there is instruction fetch, then we decode the instruction, process the instruction. Maybe there can be exception, for example, division by 0 or access of the address which is not mapped and so on. So it can be internal exception from the instruction, synchronous. Or if the instruction has no problem with the execution, then there can be external event if it is enabled from some external device. And what we need to do in this case, we need to somehow save context of the processor, which ensures that we can return back to process our original code. Then it sets up or checks for the source, for the reason, for the interrupt, somehow delivers the execution to some interrupt service routine. So interrupt service routine, for example, knows the character into the memory or informs the operating system that some block of data has arrived and so on. And And in the fact, this processing is done again by this cycle. So basically, in this interrupt processing, there is nothing else that we then read the memory, decode the instruction, process the instruction, and so on. And the last instruction of such program is some mechanism which allows to restore the state of the processor and return to the previous executed instruction stream. So we can use this mechanism for the asynchronous events processing. So again, we try to classify those mechanisms. You can find that the terms exception and interrupts are quite often mixed on this level. Okay, you know exception on the computer languages levels, it is different or connected, but little different topic. Some of those exceptions on the programming language level are in the fact result, for example, of division by zero or other events which can be caused by the actual hardware exception inside the processing of the instruction. And there is a little problem because mechanism to process the exceptions and external events is quite often combined in the processor, and some producers say exceptions use term exceptions for the external events and even for the exceptions synchronous caused by the instruction execution. Intel use the term interrupts for both. It uses the interrupts for the results of the exceptions caused by instructions, the synchronous one, and even for the interrupts coming from outside world. So be careful. Those terms basically for each producer and each architecture needs to be first understood, and then you can map them to the actual sources. But basically, if we say it a simple way, then exceptions are anomalous exception situation, and if they are the exception caused by synchronous event to the actual instruction stream and execution, then it can be, for example, the undefined instruction for RISC-V, unknown opcode. You want from processor to execute something which is not able to do. Arithmetic exception, divide by zero, but overflow, it is not used on RISC-V, but it can be a system call, which is the mechanism how the user application can ask operating system core, for example, to read or write data from file system and so on. It is our topic for the next lecture. And then the reason can be that the data are not available or there is write fault. So if you access a really bad address, or if there is an error in accessing the external peripheral, or if you do not have the page mapped to the actual address, then you get the synchronous exception. And in the case, for example, of those page faults, it can be resolved by the operating system, as we have already seen in the, I think, 4th lecture about the memory. So operating system can deliver data, for example, from disk, find the free physical memory, put their data, then add the page table, and it is possible to rerun the instruction and the program can continue. Or it can be some problem like bus error, so this means that not correct data cannot be received from the peripheral, there is some real hardware error on the bus and so on. In such cases, we usually need to stop the given process and signal the problem, or if it is in the kernel, then we need, for example, to reboot the system or stop it and try to reach the safe state or something like that for the control task and so on. And then we have those external exceptions, interrupts, events. And those can be maskable, so this means that the processor and operating system can decide if a given event should be accepted at a given time, or if it should stay only the pending and wait till we enable the exception or that source. Or it can be non-maskable, which is usually again some information about some hardware fault or software watchdog limit reach. Software watchdog is a mechanism that you set up some hardware timer which counts the hardware interval, and if you do not respond from your main loop or from your application and confirm that the application is behaving right till the watchdog expires, then when watchdog expires, it provides an interrupt or some other mechanism or reboots the system and so on to correct the state when the data are misprocessed and so on. But usually we have those maskable interrupts for the peripherals, timers, and so on. And the step for the interrupt processing are that first it is there is some list of priorities. So if it is synchronous event, then the synchronous events for a given instruction are usually processed in priority. Then there are those external interrupts and those which are not masked, then they provide and ask for the interrupt on the border between the instructions. And first step is that we need somehow to store the CPU state vector somewhere to can continue on the interrupted task. So the first thing is that we need to somehow store the state. Then a program counter is preset to some starting address, which can be fixed or it can be determined according to the interrupt source. And then the servicing routine is started, so some routine which executes the code. Again, it is same code like for the standard main program, but in this case, it directly responds to the external event. And it usually needs first to store the state of other registers on the stack, so that the state of the background task is not overwritten by the processing of the interrupt. So you need to usually store the rest of the registers on the stack under the program control. Then it communicates with peripheral, loads the data, stores them somewhere into the memory, and if it is operating system, then for example, it informs the operating system that a new data has arrived through some semaphore or some another mechanism. If it is the page fault, for example, it ensures that we return to some another task which can continue, and when the data for a given page are available, then we switch back to the previously interrupted task. So it can be a little more complicated, but basically we process somehow the exception. And if this is interrupt or exception which is recoverable, then we restore the state of the CPU, which we have noticed it at the start, and then left the processor to continue the interrupted program. And we do it through some special instruction which restores the state and restores the actual mode of the processor. And for this year we have switched to RISC-V, so we look what a RISC-V architecture provides there. So there can be some machine check bus errors, reset pins from those external, non-maskable interrupt, hardware interrupt, and for the synchronous, there can be some address error, undefined instruction, system call, breakpoint, and so on. And now we go a little more deep how it is actually implemented. It is simple example, but it is, even that it is simple as much as possible, it is relatively complex. For sure, you do not need to remember for the exam actual name of the registers, the numbers of the registers, and so on, but you should know the concept. So, on the RISC V, we have those 32, or in the fact 31 plus fixed 0, general purpose registers. Then we have there, we can have there optional floating point registers, again up to 32. And then we have there some control status registers. Those control status registers are accessed as a numbered registers. It is used the I format to access those registers, where immediate 12-bit part of the instruction in the fact doesn't define a constant, but it defines a number of the register. And so we can have up to little more than 4,000 of such registers. Usually not all of them are implemented, only a small part. And we look there at those which allows to process the external events on the machine level. So all of those start by M, because usually processors which should allow separation of the more user application needs to have a more states modes, protection modes. One for example, at least one for operating system, which can set up paging, memory, control the interrupts, stop the interrupts, map the pages, and so on. And then there has to be the another mode which is intended for the actual user program run. And in this case, all the privileged instruction has to be blocked. Because in another case, your actual code can set up a page table and access, for example, memory of another process which runs for another user, and you should not be allowed to access it. So for this reason, you need at least two protection modes. But on RISC-V, they have decided that sometimes you want to use even the virtualization. On x86, you have in the protected mode, you have 4 modes, 4 rings in the 32-bit mode. Only a 2 system and user has been left for the 64-bit mode, but then additional priority modes has been added for the virtualization. So it is quite complex. On x86 it is quite complex. On the RISC-V it is defined that the CPU start in the M mode, in the machine mode, so all those registers start with M. Then it is possible to switch to system mode S, where is running operating system, and then the actual user mode, where running user application. So, but we now look at the processor, which maybe doesn't need even to implement small microcontrollers, doesn't need to implement the other modes at all. So they start in that hard real machine mode, and we look at interrupt processing at this mode. And we have there this subset of the registers described. So the first one is machine status. And machine status allows to know in which modes you have been run before, allows to mask the interrupts, and so on. Then there is another register which can be used to know the actual set of the instruction set extension which are active and which can be used. So this is the ISA extensions, where each bit represents some extension. Then we have the machine interrupt enable register, where you can select for those external sources if the given request should result to the interrupting the processing, or if should it stay only to be pending and it will be processed later. So we can use this mask in the fact, which enables only subset of the interrupt. Then we have there empty VETS register, which holds a starting address where interrupt handler or exception service routine starts. So it is the actual address where the execution will be transferred when the exception is processed. And there is one problem, that if we get to the exception, that we want to store the state of all general purpose and floating point registers, that we can restore them when the interrupt processing finishes. But there is one problem, that we, on the RISC load store architecture, we can store data to the memory only through the use of general purpose register. But if we want to use a general purpose register to store the state of other general purpose registers, then we need the first to rewrite one register, but we lose its value by the rewriting to store there the address where we want to store the rest of the registers. So for this reason, we have there a special register which is used only to temporarily store the value, or maybe temporarily or even longer, of a single of the general purpose registers, which allows to set it, that register, to the address where we store the state of the other registers. Then we need to know which instruction has caused exception. So if it is the exception caused directly by the given instruction, for example, invalid access to the memory, then this register keeps the address of that instruction, and when we correct the situation and return to this address, then the given instruction will be re-executed, and maybe we get a correct result or another exception. Then we need to know what is the cause, what is the reason for a given exception, so it is mcause register. Then we have their empty value register, which is usually the address, memory address, virtual memory address of the location, which, for example, cannot be read or written, or the instruction cannot be read from, and so on. So it is some information which is connected to a given exception type. Then we have there already mentioned machine interrupt pending register. So those there, each bit informs, okay, there is, for example, keyboard asking for the interrupt. And it can, but need not to be accepted according to the mask in the interrupt enable. And then there are some another registers which helps the processing and identification of the source of the exception. All this in the RISC-V case is described in the second volume of the RISC-V architecture specification, which specifies the privilege part of the architecture. And it is great that on RISC-V everything is on in the gates and freely accessible and so on. So it is great architecture, and even Intel and IBM and others use the RISC-V. Okay, IBM tries to push PowerPC still, but Intel uses RISC-V and many other companies use RISC-V. NVIDIA use internally inside the GPUs RISC-V for the management, and in your SSD disk is RISC-V today, so it is quite useful architecture already. Okay, now if we look at the actual registers, so M status register that with index 300 hexadecimal, then this register has this set of the fields. We look only on some of that which are important for our case. Those which are marked W, P, and R, I means that they are not defined by the architecture yet, but they are reserved, and you need to write there the value which you have read already from this field, so you should not write anything else than what was there previously to be compatible with future version, and when you read the value, it should be ignored. And what are there bits? There is interrupt enable for system mode, we do not take care about it, but what is important, there is global interrupt enable for interrupt on that machine level of the interrupts processing. You see, they are speaking about exception, but the register is interrupt enable. So you see that even RISC-V specification intermix use of exception, trap, and interrupt. But in the fact, this one is for the external interrupts. It cannot block the actual exception processing. So maybe it is correct, because it is for the external interrupt. For the exceptions, you cannot block them. So if you have the another exceptions inside the exception processing, then it is usually some fatal error and your operating system stops there and so on. But for the external interrupts, it is quite common that a new source starts to pend during the processing of the interrupt, and you have a problem. If the interrupt processing routine is interrupted again, then basically you lose some part of the state, because you have there, for example, that EPC register, but it is only once here. So if there comes another exception, that it overrides the EPC, and you do not know where to return. So you cannot allow without some. Okay, you can store the previous state and then you can allow nested interrupt. But at the start of the interrupt processing, you cannot allow the yet another interrupt processing to interrupt this interrupt processing. Okay, it is a little complex. So for this reason, there is that global interrupt and a machine level previous interrupt enable bit. So at the moment when interrupt arrives and starts to be processed, the previous value is copied to the previous interrupt enable, and this one is set to the 0. So this way it is ensured that recursive processing of the interrupts out of control of the operating system or processor is not possible. Then it is information about previous privilege levels. So if, for example, the interrupt comes when the processor is running user mode, then in such case we store their information that exception has arrived from the user mode, and that we know that when we will end its processing, we should not return to the machine or system mode, but to the user mode. And there are much more fields, but those are those important. Okay, then we need to have the register where we can read the actual information, what caused the actual exception or interrupt processing. And for this there is mcause register, machine cause register, and most significant bit, which can be on the 32-bit architecture, bit 31, on 64-bit it is 63. Then this bit informs if it is internal or external event, asynchronous event. Why bit 31? Because you can easily compare the exception register against 0, and if it is negative, then you know that it is interrupt, and if it is positive or 0, then you know that the source is the synchronous exception. And the rest of the register can hold the value of which informs about the exception code. And okay, usually not all the 30 bits or 31 bits or 62 bits are implemented, because the number of sources is much smaller. So there is only some subset, some low 5, 10 bits used as a source. And this number, which is in the exception code for the external interrupt, corresponds to the bit position of that source. So basically this is a shift left of 1 in the registers machine interrupt enable, machine interrupt pending registers, and so on. So directly this number corresponds to the bits location. And if the MSB is clear, then it is the synchronous exception. And in such case, when you, for example, correct the setup, then you can return with mret. In this case of the external interrupt, again, you can continue the program by mret instruction. But if, for example, the reason is syscall, then you do not return again to the syscall because it would invoke you again. So basically, in this case, if you process the syscall, you want to continue by the next instruction after the syscall. So in this case, it is in the RISC-V, it is called eCall, environment call. Then, in such case, you need somehow to advance EPC to point after the instruction causing the exception processing. Okay, so this is the registers. Now the source. We have there those exceptions which can be source. So for example, it can be a misaligned instruction. So even if you have a RISC-V which can process the compressed 16-bit instruction, we have look only at 32-bit. Then if you try to execute the instruction from the odd address, then it is invalid address, and the response of the processor is misaligned instruction exception. If you access the address, attempt to read instruction from the address which is not mapped, then you get, or which is not executable region, then you get access fault. If you attempt to execute instruction which is not known for a given core, then it is illegal instruction. You can have there a breakpoint instruction. It is e-break instruction in the fact, which allows to stop the execution. Then you can have find that the load is misaligned if you have the variant of RISC-V or such setup which doesn't allow a misaligned access, for example, a 32-bit value on the odd address starting and so on. If the, for example, 32-bit values has to start on the address divisible by 4, then if you try to access incorrect address, then you get this exception. If you cannot load the value due to the page fault or some another problem with the memory, then you get a load access fault. If it is a misaligned write or atomic operation, then you get 6. If it is the incorrect mapping of the page for the store operation, then you get 7. When the user space wants to call the environment, then you get 8. If it is from the operating system, a call of the machine mode, then you get the reason 9. If it is called from the machine mode, that you get 11. For the actual instruction page fault, you get 12. Load page fault, 13. So basically, if there is a problem with traversing the page tables and so on, store page fault, and then there can be some another exception which are specific for the concrete implementation. So those are those synchronous which are caused by the actual instructions. Then we can have those asynchronous, and those are the external interrupts, and it can be, for example, interrupt by the software from supervisor, machine, and so on. And then we can have there interrupt from the timer on supervisor machine level, supervisor external and machine external, and then we can have there some platform specific sources. So for the next example, we will consider that interrupt 16 is connected to the event that the serial port receive Rx the character. So this is our in the next example. And this register machine interrupt enables individual source bits for those external events. This register informs which are pending, which doesn't mean, or those are which waits till they will be enabled, or till the global interrupt will be enabled. And at the moment when the interrupt is enabled on both levels, then the interrupt processing is invoked. And there are different set of the registers for the system mode and so on, but we will not look at those at this moment. We stay on our machine mode. So what happened, for example, okay, and it should be not syscall but ecall on the RISC-V. So what happens when ecall is received, or when the interrupt or exception starts to be processed? The program counter, which points to the instruction, is copied to the machine exception PC. And the processor switches from a given privilege mode to a machine privilege mode. MPP of the status register is set according to the previous privilege mode. So from this you know what was the preceding privilege mode when you want to return to the code to restore the correct code. And the mCause register is set according to the source of the exception or interrupt by the code, and if that x length, so it is the length of the registers -1, so 31st or 63rd bit is set, then it means that it is the external interrupt. Previous interrupt enable is set from the actual machine interrupt enable, and machine status interrupt enable is set to the 0. So this prevents that infinite recursion of the interrupt processing. And a program counter is set to the address where points empty VATs. And what we can do inside such interrupt processing code, we need to find what was the reason. So we can use a special set of the instructions which allows to read a control status register. So it is instruction CCRR, means control status register read, and we can read it to standard general purpose register. For example, we can read that cause register and determine what was the reason. We can use a read-write combination CSRR which first takes the value of the control status register, the preceding value, store this value to the general purpose register, and then set the value of the register to the value of some another general purpose register. We can even set the immediate value, but immediate, because we use the immediate field to select the actual register. So in this case, immediate value are only the 5 bits, which normally represent the RS1. So it can be only the 5 least significant bit of the register can be set directly by the single instruction. We have there the option to do a set and clear. So basically you can provide a register, general purpose register, which defines a bit mask which should be cleared or set in the control status register. And you can read the previous value. So you, for example, can disable the interrupt, but get the information what was the previous state of the disable of the interrupt. You can even use those combinations to set and or clear bits with immediate 5-bit value. And then there is a pseudo instruction which allows to only the read register. So conditions control status register read, and it is defined that a write is with the register x0. So in the fact, because it is a fixed 0, this value is not applied to the control status register, and we only read the value. Other option is that we can only the write value. So in this case, we say that the result should be discarded, and we can say that it writes the value in this case of the register. Okay. Okay. So, and when we want to finish and return from the exception processing, then we can use a machine level return instruction, and it restores the privilege mode to the previous one which is stored in the machine status register, clears the machine status previous priority field to the 0, and sets interrupt enable to a previous state of the interrupt enable. So this allows atomic in the fact enabling the interrupt at the moment we return from the interrupt processing. And the last step is that a program counter returns to that address of that instruction, which is the first one unfinished in the instruction stream of the main program, background program. There is one important thing, and it is precise exception processing. If you want to be able to, for example, correct the situation when there is a page fault, then it is necessary to deliver or set the state of the processor such way that you can restore the whole state. But if you imagine that, for example, instructions are executed out of order, then in such case it is quite possible that, for example, some instruction has already finished the execution and has its data, and in the theory can try to attempt to write to the main memory, and only after that some preceding instruction, which, for example, causes a division by 0, causes the exception. And if we allow the instruction, the later instruction, to modify the actual memory, then in the fact, if there is an exception, then we cannot restore the state later of that processing of that instruction, basically, because already some future instruction has modified the state of the processor and the memory. So for this reason, today processors execute the instruction out of order, but actual effect on the memory is postponed till we know that no of in-program order instruction of those preceding instruction didn't cause the exception. So if the exception processing is precise, then you know that your exception processing exactly started on some boundary of the instruction, or that this one is last which has been attempted but not finished. So it allows to operating system to correct the situation and continue then later after the correction of the situation. So it is very important. If you do not have precise instruction, precise exception processing, then you cannot implement a page paging and swapping correctly. Okay, you can, but it is extremely complex. For example, on 68,000, the first chip from this family of 32-bit processors, they did not have the precise exception processing. So when the processor has been equipped by external memory management unit, and that signals that basically you cannot access the memory because the page is not present, then a processor was not able to resolve the situation. So there was one operating system and hardware where they solved it such way that in such situation they stopped the clock to the processor, started another processor which does actual loading of the page from the disk and correct the situation and updated the page tables and set up it in the memory management unit, and then later enabled again the clocks to the main processor. So as you see, it is extremely complex. On today's processor, if you have the precise exception handling and processing, then the state can be safe on that actual core and it can start to solve the page fault, and then when it is corrected, it is possible to continue. Okay. So, what we will do if we want to see how the exceptions are processed on RISC-V, we can have the processing of the exception in so-called, again, pooled mode, where we have only a single target address where all source of the exceptions continues the execution. So there is single interrupt or exception servicing routine, and it decide what is a reason according to mCause, register on RISC-V, by the software. So it is software processed and decision making and routing of the events. And this one, in the fact, is sometimes better than other options, because on the operating system you usually need to do some common processing for even for all external interrupts. So it is better to have a single entry point and process all the exceptions and external interrupts at the single entry point. On the other hand, if you have some small MCU microcontroller which should process a different exception or interrupt sources very quickly, then it can be better to directly start the execution of already specific interrupt service routine for a given source. So in such case, you can want so-called vector interrupt or exception handling, which is, for example, used on small Cortex-M MCUs. You have there the area which start at a vector-based register or at some area in the memory, and there are 4 bytes where the CPU should start after the reset signal. Then it follows by another 4 bytes what should happen at some exception cause. Then there is area where is directly the address where should be processed the interrupt from the serial port and from the control area network controller and so on. So basically you have vectors in this case, which gives you much faster to the actual routine which process a given event. On the other hand, if you then want to handle a switching of the task and so on in the operating system, it is much more complex to have that vector base. So it is question for different application is better a different option. We can have a non-vector one with different addresses that you know, for example, that for the exception on RISC-V, it is possible to set up mode that for the exceptions, all exception processing start on single address, and then for each external interrupt source, you have another address which is set to the program counter at the start of the exception processing. So there are different options, but you should know that there can be masked and non-maskable interrupts. Processing can be software, in the software, or it can be a vector in the hardware, or it can be some combination. And now there is the actual code. How will look such processing on the RISC-V? So we have there some start address, and there are some set of the values to the A0 to know which instruction has been in the fact processed and which not. And then there is a first test. We know that our processor and emulator start in the machine mode. So in this case, we can set exception PC to some address. So we load address of this label in the program, and then set it to the machine exception PC. And if then we invoke the mret instruction, then those two instructions should be skipped, because it is how the machine return should work. Okay, so it is only the test. Then we can check what is the actual value of the machine exception PC, and there is e-break to stop the execution. So it is only to test what can be done. Then there is a rest of the experiment, and it tries to set up a simple echo of the external incoming characters from the serial port again to the serial port. So basically we want to run some background task. In this case it will be a light snake on the LEDs. It runs in the round. It sets one LED after another, and when there is incoming a character, then without the pulling of the status register, it should read it and send it back. If we add there the line editing and then the operating system and shell, then you can start with the whole operating system from this point. Okay, so what we need to do? The first, we need some address where we want to process our exception. So it is the address which is called handle exception, the label. We set it to T0, and then we set the empty VETS register to the value. Then we need some space where to store the state of the registers during the interrupt processing. And I have used in this case mscratch register, that additional register, that it will store at the start of the interrupt the address where to store the rest of the data. We will see how it is done later. Then we need to enable interrupt on that global level in M status register. Then we need to enable our source, which we have said that it will be a source 16. So it is source 16, but we need to use it as a bit mask to enable it in the interrupt enable register. So in the fact, we take there 16, there is a 1, we shift it to the left by the 16, and then we do in the fact MIE or this T1. So basically we set the bit which corresponds to the given external source. And now we start to work with the actual serial port. So we take the base address of the serial port. And in the receiver status register, we need to enable the interrupt not only on that global level and level of the processor, but on the level of the peripheral. So we enable there by the write to the status register bit 1. We enable the interrupts. And now there is a background task. So we do not take care about serial port anymore. But there is a background task. It sets the ones to T0. It sets the start address of the SP-let region. So this is that region where we can write to the let output. This is only to check, to look what happens in MPC, to know that there is some exception. Then we store the value, so one let is lit. We shift it to the left. The most significant bit is set to the bit 0. So basically we ensure that there is one bit rotating through all the LEDs. Then we read setting of the knobs, RGB value, store it into the one LED. Then we negate it and store it to the another RGB LED and continue. So it is background processing which doesn't know and doesn't care about the serial port. But at the moment when the character arrives to the serial port, then the exception is invoked in this case. And the first instruction switch the scratch register to the with the thread pointer. So this way we have in the fact preserve the user thread pointer in the mscratch and take a previous address which we have prepared it here in the scratch, the pointer to the task control block. And we store at the different offset those registers which we want to preserve from the application to not be changed by our interrupt processing. Then we read the cows from mcows register and check it against a 0 to know if it is external event or a synchronous exception. If it is less than 0, then we go to interrupt processing. If it is smaller than 0, if it is positive, it is bigger than 0 or equal to the 0, then it means that it is synchronous processing. In our case, we do not do anything in this case, so probably it will end by the crash of program because we do not know what to do there, for example, with the paging and so on. So there would be the operating system routines. We do not have them here. So we try to return and see what happens in this case. So there is a restore of the individual registers from the task control block. Then we need to restore the last register, that thread pointer, from that value which has been stored in the scratch register. And we put back to the scratch register the value of our pointer in the fact to task control block. And then mret is invoked, and this instruction ensures that the PC returned back to some of those instructions where there was interrupt in that background task. Okay, so it was all the other sources of the interrupt which we do and the exceptions, but if we take care about the interrupts from the peripherals, then there is actual handling of the interrupts, and in it I have decided to do it such a way that I shifted to the left the cows, so it means that I multiply it by 4, and in the fact most significant bit, that minus which informs that it was the interrupt, not the exception, then this one is shift left from the register. So at this moment we have there a cows multiplied by 4, which in the fact can point directly to some table with pointers to the handlers for the serial port, receiver, transmitter, and so on. So it is so easy to decode the source and then call directly the function. I do not have there the real table and so on, but I only compare it with the 16 multiplied by 4 if it is actually our character receive interrupt. If it is, then we go to the actual echo processing. If it is not, then it is best to mask out a given source, because if we have not processed it and not clear it in the pending Then at the end, at the moment when we try to return from the exception by the mret on the previous page, then it would invoke the interrupt again. So such source, which is some spurious, unhandled source, can be masked also. The solution rotate back the cause, but in this case without the most significant bit set, because it is logical shift right. We use it to shift the one to the left according by the cause, and then use this instruction which clears the given bit in the interrupt enable, and then we go to the return from exception on the previous page. If it is from the serial port, then we get to actual processing, which is quite easy. We can directly use this register because it was previously stored on the into the safe area. So we do not need to take care about the storage here. We know that we can directly use it. We read the value from the serial port receiver data register because we know that it caused the exception, so we can expect that there is a character. We should wait till there is a space in the output one. I do not do that there and directly write to the serial port and send the character to the output. And then we return again through the common return from the exception over here. So relatively easy. You do not need to remember, but you should know a little how it works. The complete example is here for the simulator, but the exception processing is not yet finished fully in the simulator. So, but in the next version it will be available. So those are the exceptions, and we can have there those reset, non-maskable interrupts from the peripherals, synchronous different overflow traps, and so on. On different CPUs, it can work a different way. Quite often, we want to have there some timers, which provides timing to switch between different tasks, or that given time has expired and we should do something. So we can have there, for example, a mechanism which is connected to the real-time clocks, to the wall time, and said that at given time we want to receive the interrupt. Or there can be a timer, and we can say after so many microseconds, nanoseconds, we want to have there the event. Or there can be that watchdog, which is set to provide a non-maskable interrupt or reset of the system if the application do not respond in some predefined time. So it is a mechanism to check for the misbehave or some overload of the system and so on by its reset or notification. Okay, so it was for the actual example, and now we try to look, for example, this is for x86, how we can work with the actual data. So one possibility is that real pooling. So again, we return in this case, but in case of x86, to the state when we try to read the sum status register and test it if there are data. So this is that mechanism when we waste a big amount of the computational power and time to wait for actual data. If there is a bit set, then we process the data and do something with those data. So this is that pooling. Then we can have a little better solution when we wait for the data, but not pull directly on the status bit, but set up interrupt, and instead of pulling, we use there a halt instruction on x86. So this way, the instruction execution stop, processor lowers the power consumption, and when the interrupt arrives, that at that moment we read the data and store them from some peripheral, and informed by some flag that data has been read. And in this case, it works such way that processor stop on the halt instruction, or in ARM it is called a wait for interrupt instruction. And at the moment when the interrupt arrives, the processor is woken up and the data are read, and we can find there the data, process them, and do something like this. So still we cannot switch to another task, but at least we do not waste a power. But we usually want to switch to some another task. So this is how it works in the Linux kernel, for example. This is an actual piece from some of my code, but it is simplified again. So in the Linux kernel, we define that there is some white queue, so some list of those which waits for a given event, interrupt, and so on. Then when some for example, a driver, if you want to read, for example, from the serial port. So internally, after the finding that it is serial port and so on, the read operation from the user space, and in this read function specific for the serial port. It knows that it should store the result in this buffer, that so many bytes should be read, offset is probably ignored, and that it is corresponding to this file pointer. And what we do there, we set up first usually somehow that we want to get the interrupt and so on, but it is usually done at the open time. And now at the time when we want to read it, we say we want to wait for the event when there is the interrupt pending or data are available. So if the data are not available, we want to wait for event. So this is negative condition. When there is no event, then we want to wait. And we say we want to wait on this white queue. And at the moment when character arrives, and through the interrupt processing, something like you have seen on the RISC-V, for example, is invoked this C function, and it stores the information that given character has arrived, stores it somewhere, and so on. And at the end, it says, okay, the event is pending, and notifies all tasks which are waiting on the white queue that they should be woken and process a data. So basically, your task goes there, stops, CPU is used for another task, users and so on, whatever is there to be done. At the moment when event arrives, then it is processed, white queue is enabled, event is set, so we do not wait anymore here. We check for some errors and so on. And if the data are available for the user, we copy a data from the internal operating system buffer to the buffer of the user. So we copy the data with some check, because it is necessary to check that you do not overwrite incorrect memory address and so on. And the length is returned. So basically, you really see what happens if you try to read from some device file. It is same on Windows, on Linux. On Windows, it is a little different, the structure of the code, but the mechanism is same. What is important that we usually want to implement it with white interrupt table, because it means that if you try to kill the task or send the signal to the task, then if it is waiting with, or it can wait with timeout or without timeout, that when it is, because if you do not have there the interrupt table, then if a given task waits for some event and this event didn't arrive, then you cannot stop that task. Basically, it will be indefinitely blocked in this kernel mode, and you cannot stop it. So for this reason, usually the stuff where it is possible that the event didn't arrive for some external reasons should be marked with this interrupt table, which answers the ability to break it. So it looks generally like this. Your user space program tries to read from the device, for example. It invokes system call. System call checks if there are data or not. Probably it previously set up the hardware. If there are no data, it set up the hardware that we wait for the interrupt, and a given task on that wait for event is stopped, and it is rescheduled to some another task. So other processes, task, users, graphic, and so on is running. When the interrupt arrives, interrupt handler process actual event, wakes through the wake queue kernel part of the process in the kernel mode, and it copies a data to the user space buffer, and then it returns through the syscall return to the user task, and it gets data. So it is how it works generally. Okay, then there is yet another example. It is on RTMS. By the way, now the RTMS is looking for the students for Google Summer of Code. Maybe I will be invited to solve there some control ANRA network controller implementation with some foreign student. So in this case, it is from our SD card driver from the infusion pump, and you can see again, it is read from the SD card, very simplified. We set to the device driver that a given task is waiting for the event. We say we want to stop and receive for the event, and it can be error from the SD card or some another event and so on. So it can be MSD wait event, so standard or error, those situations, and that we wait till one of them is available, and we wait for some number of ticks, and we want to know which event has happened. And the task is stopped, and for example, a graphic update is running in parallel. Then SD card delivers data, and at that moment, this interrupt handler copies data somewhere. It is not important at this moment, but it knows which task should be woken up and send it the event. And it can then process data and mark the request for the access the SD card as done. So it is yet another possibility. Another possibility is to use the semaphore. So in this case, we have there set up the semaphore, and the actual wait for the event is implemented through the operation wait for the semaphore, and interrupt handler, if the given condition and data are available, we set the semaphore, we release the semaphore, and the task can continue. This is, again, it is very similar. It is from my driver for the Windows port. So in the Windows, it is a little more complicated, but anyway, you connect the interrupt source to a given handler. You say which vector, which number of the source it is. You can select there some another interrupt levels and so on. If it is ISA, it is shared and so on, it is on which CPUs the handler can be run. But anyway, then when the interrupt happens, you get to the interrupt service routine, it does something, and then continues with different procedure calls. So it is possible, for example, in this case, to register some routines which are run in the not at the user or system level, little higher level, and dispatch level, uninterrupt table level, but not directly in the interrupts. So it is another option. Now, if we do not want to process each data byte, we want to use a DMA. In such case, we can have there a peripherals, we can have there a memory, and the processor. And processor with operating system set up the peripheral, for example, this controller, to read some sector, and it can use, for example, a DMA controller to respond to the request to store data from the disk to the main memory. So in this case, we only set the request which data should be stored where, then peripheral informs the DMA controller there are data, DMA controller sends a bus request signal. It is for the shared parallel bus. Processor finishes the instruction, responds that it disconnects from the bus, informs that it grants to the controller the access to the memory. Controller, if this controller doesn't need it, this is so-called daisy chain setup in this example, then it can pass the possibility to connect and move the data and control the bus to some another controller. But if this one wants to reuse it, it says okay, bus request, and this way it gets information. Bus is busy, so it allocates the bus, address the peripheral, reads the data from the peripheral, then stores the data to the memory, and then it finishes bus request and bus busy signals, so processor can continue. And when it transfers all the desired data, then it informs by the interrupt, not that single byte is available, but that all bytes of the given transfer are available. And it can be even more complex if we have multiple levels of the buses. Exactly what I have shown on the previous one is there written in the text, so you can read it yourself. Today, the DMA controller on the bigger systems are not part of the integration. On the small MCUs, there are usually some DMA channels which are part of the integration of the processor. On the bigger systems, the controller and DMA controllers has moved exactly to the actual disk and network interfaces and so on. So in this case, you use for example, a PCI bus, set the where should be a packet, where is a packet ring of the buffers to store the incoming packets, and then processor doesn't need to take care about the actual data. They are stored to the memory from the network controller, and when the whole packet is ready, it wakes the CPU. This one wakes the controller wakes the CPU through the interrupt, and CPU reads the data from the memory, and so on. So those are the possibilities. Again, there are different setup how it can look. That it is slow when you respond to the actual interrupt and process data in the interrupt, so you want to do that in through the DMA. And you can have even some input-output coprocessors. In the fact, the whole GPU is in the fact only coprocessor to the main operating system, so you can look even on such complex stuff as input-output or GPU coprocessor. And each time it is same that processor somehow notifies the peripheral, sets the transfers and so on, and then left to do the actual transfer by the hardware. Again, there is the examples. It is multiple times shown here that if you go through the slides yourself, that everything is described. But there are some big pitfalls. Do you see some real problem in those stuff? We have spoken here about the communication and so on, but there is one significant problem. What do you see there as a problem? Do you see on this picture some significant on this one? Again, some significant problem. We access the memory from the controller, from the through the DMA. Processor wants to access the memory as well. It wants to access it fast. So to access it fast, it has because we do not have a fast memory, it's not possible to implement. We have there a cache. And it is a problem, because if we access those data directly and the processor has copy in the cache, then it is possible that it doesn't see the changes which has been delivered from the disk, for example, or it sets the changes only to the cache, but not to the memory. So first problem is the cache. The second problem is that today processor executes the instruction out of order, and it is possible that they reorder the actual read and write operation to the memory. Because for the speed up, it ought to be done this way. Each architecture has different rules. It is really, really complex stuff. It is probably most complex. The memory models are probably most complex part of processor system design and then programming. This is Paul McKenney from IBM. We have him here for a real-time Linux workshop some years ago, and I have contacted him more times. So this is one, and maybe he has done even the modeling of those problems with one former student. She is called, I'm not sure for the first name, but Aglava is, I think, the name, and they have built a model, how to model this asynchronous access of the memory from different operating system and so on. And you can put the synchronization barriers between instruction on the processors. There are different, for example, on the RISC-V, it is the fence instruction. And you can put all those fence instructions everywhere where you can expect that there can be a problem, that the data can be modified out of order by the processor. But then the code will be extremely slow. So basically your task is to find as little places where it is necessary to put some synchronization, and so lightweight synchronization which is possible, but still ensure that the data are consistent and correctly processed. And it is really, really hard. And there are two levels. One problem is the cache, and one problem is out-of-order execution on the processor level. So for example, for PowerPC, if you do not put this in-order execution of I/O enforcement instruction, then the data do not reach the peripheral. I have tested the PowerPC, small PowerPC for engine control units. I have programmed there a loop with a volatile, which ensures that the processor blocks for some while. Then I have put there a write, again with volatile, to ensure that, do you know volatile modifier for the, we have already spoken about it, I think. Volatile for the pointers to some variables. Because this way you say that the given access should not be optimized by the C compiler, that really there has to be store word, load word instructions, that it is not possible, for example, if you read twice from the same memory location, that it cannot be only the single load word instruction. Even that you do not write between that, because it is possible that it is some another thread or some another DMA and so on writes in between. So you can say it is volatile. It is something which can change out of control of the processor. So even if you put a volatile modifier to the actual access, then you can get to the state that the actual data has not been delivered to the port which controls the LED. So I have written the code, it was correctly written, run it, LED didn't blink. And when I use the debugger, I see, okay, processor is executing the code. Because the processor kept the written data in write-back buffer, and because it doesn't need to write too much to any other location, it was simple code, then basically a change has been stuck inside the CPU and never appear on the external bus and on the peripheral. So you can use this to ensure that the data are enforced to go out to the preceding outputs go out, and following inputs cannot be fetched earlier than after this instruction. So basically it is the barrier which disallows reordering of the instruction. So this is one problem. You can, if you want to write a Parallel programs. You want to use threads. Today, your throughput of the single core is would not increase too much. So if you want to write an application which process some bigger amount of the data, you need to write it as a multi-threaded to use the huge number of the cores which can run in parallel. But in such case, if you modify some data and then, for example, you confirm that the data are ready for the other thread, then you need to ensure that that flag which marks the data that they are ready for the other thread is set as the last one. Because if the second CPU sees first the change of the flag to the ready, and data are not yet visible to that second processor, then in such case you start to work with incorrect data. Very easy to make real mistakes in the multi-thread programs. So, in this case, you can use so-called memory model, and for C++, the memory model is defined as the relaxed atomic operation. So in this case, if you, for example, do the atomic add, in the relaxed mode, you are sure that the add will happen, even if you run it in parallel. Because if you run, for example, in multiple threads, add of the A, of some variable, and you add from the multiple programs, you write this simple code. And it should, for example, count a number of each of the threads, for example, counts a number of the people in one district. And you write this code that you want to speed it up, and each of them should add the values of the person in the some global variable. It would not work. Do you know that? It cannot work, because in the fact this code is translated as the load word to some register, then add one, and then store word. But in between, some another thread can load the word, add the value, store it, but you add the value not to the last one, but to some preceding value. So basically, the count of one is overwritten by the count of some another. So basically, you start to lose the increments. At the moment when you use the atomic operation, which is there is atomic add operation in the C++, then it starts to work. And you can use relaxed. In this case, this means it is independent global variable where I want to, for example, add the value. Then you can have acquire and release. So basically, if you want, for example, to set up data, and then do atomic write to some location which confirms that all those data are ready to be processed by another thread, then the last access to that variable which confirms that data are ready should be in the model release. This means now all preceding writes are ready for somebody else to be seen. Same for this one who wants to read the data. It should check for the location which confirms that data are ready in the memory model acquire. This means, this ensures that if you get the one in the acquire mode, for example, the data are available, then it means that all preceding writes from the other processor which has been before the release will be visible by the loads war operation after the acquire succeed. So basically, this is a memory barrier which allows to send and receive data. Then you can combine acquire and release, or you can use a completely sequential mode, but it is very expensive. So for the atomic operation, again, you want to find those least heavy one to make your code fast. In the C code, you can use those are those memory models. I have written there a little more about them. It is important thing which you should know. ask this at the exam too much, but it is really important. So, and you can have there, for example, load some variable in the model, relax it, so it is independent from some another, completely sequential or acquire. So in this case, you can check if the data are there. Or you can store, and store in the acquire has no reason because you do not check for anything. Store is only to store something. So it has a reason to be in the model relax it, or for example, release that you confirm by the write some another data. Then there is the exchange, that you can switch some data between the register or some local variable and between the location in the memory. And this one is atomic, so this means that no swaps in the between happens, only the single one, so you know what is there. There can be the exchange, and the most important operation for all those atomic processing and so on, which can be used to build all others, is compare and swap. Compare and swap operation allows you to, that you first load the value from the memory, do some processing with that value, for example, at the one, and then say, I have a new value which I want to store to that location in the memory. And if there is still the previous value for which I have done the processing, then in this concrete case, store the new value to that location. If somebody else has already modified the location in between, then in that case, the operation fails, and you know somebody else has tried to do something there. So basically, I need to read a new value from that location, do a new attempt to compute my increment or something, and then attempt again to store the value. So this is the compare and swap operation, and there are different operations which can add, for example, this add the value and that fetch a result. Or you can fetch the value and ensure that the value is incremented by the given increment at the location. Or you can test and set bit. So basically you test if given bit has been set at the given location and set it to the value and so on. So those are a mechanism which allows to build all a higher level construct like semaphores, queues, and so on. So it is, and it is interesting that, for example, a gmake, when you increase a number of cores, can utilize a bigger number of cores. But for example, exim, in this case it is older example, it is from some article, then your boss said, okay, we have new users, we need to increase the throughput of our system. And you say, okay, we buy a bigger server which has 42 processors. And we will serve about 50% more users. No, you buy the new processor, it has more cores, and what can happen is that you start to see a drop on your throughput on the level when you have 6 processors. This can happen, basically. This is the problem of the application, and you need to think how the synchronization works because you can lose the throughput. This is the time which it takes to do a single read on the location where n threads tries to read that location and only one is writing. So even in this case, the read operation degrades because as there is more cores which try to read the same location, then the cache lines start to cycle between all those threads, all those cores, and even single access is slower than if you have no such collision. So for modern application, it is best if you have application which on one core, for example, reads and writes and reads, and it has no interaction with other cores. So if you work with your own local memory on a given core, everything is correct. If you work with the data on another core, okay, it is correct. If you read the data by both cores, it is still correct because the caches allow to set a model where the data are shared if they are not modified and they are propagated to multiple caches. But at the moment when even if only one wants to read and another wants to write, then you have a trouble. So you need to minimize those situations when two cores access the location which is modified by one of the cores, and if both tries to write, then it is the worst situation. So basically, the message is that, for example, use linear arrays, they have no problem. Use the hash tables. Binary trees, which I like a lot, has a problem on a multi-thread application. Use read copy update, which is invention of that Paul McKenney from IBM, which is used in the Linux kernel, but it is used even in the user space. It is the reason why CZ-NIC, Czech internet servicing company, domain name servicing company, is the fastest in the world. They know how to use those modern mechanisms in their DNS resolver and server. You can prevent a pessimistic operation by optimistic check. So basically check if the situation, or try to do some situation, process it, and then only at the end check if the actual pessimistic situation happens, and in such case redo the operation, for example, and so on. So those are the possibilities how you can speed up your code. For sure, if you have the target where you need to ensure DMA consistency, then you first thing is that you need somehow to ensure that consistency on the level of the processor and wait back queues and so on. On the x86, there was no think about this when the architecture evolved at the start, because it is the architecture from 1980. So it has no such instructions. So there are some instructions which has normally empty effect. For example, swap top of the stack pointer with itself, and this operation is used like a memory barrier. So there are strange opcodes which are reused to ensure the memory barriers, but you need to use them even on the x86 to ensure that your code executes correctly on the modern CPUs. On the other hand, x86 has advantage of simplification, that it doesn't utilize out of order writes, so it keeps the order of the store operation. It is total store order preserving architecture. So it makes the stuff and think much more easier. But reads can precede, they can be swapped. So in this case, you need to use those special instructions to ensure that they are synchronized. On RISC-V and another architectures, you have the mechanisms to describe actually the barriers. And for example, for the caches, if you do not have a coherent cache between the peripherals and CPU core, then it is quite complex. On ARMs, it is not coherent usually. So you need to ensure that on operating system level, you need to flush the caches before the memory location is accessed from the peripherals and so on. For example, on PowerPC, this is set of different operations which allows to flush and maintain the state between the main memory and cache. You see this set of some, 15 operations at least. On the ARM, there is quite a large set as well. On the MIPS, it is cache operation. On the RISC-V, there is fence operation for the synchronization between the core and cache, but for the DMA, they use a coherence between the main memory and peripherals. It is similar for the x86. It has, in most cases, coherent behavior between access from the GPU and the peripherals to the main memory. And it is all for today. So thank you for your attention.